I was going to say that hot air balloons are cool, but they're not. They're hot. Hot air balloons. Why? Why does a hot air balloon work? So here you've got the basket, and there's some sort of a burner in here that's heating the air. That's why it's called a hot air balloon, because it's got hot air in it. And the balloon goes up in the air. It seems like almost magical. There's no helium generator or anything going on here. When we heat a gas, what does that do to the movement of the particles? It increases their movement. They move faster. That will cause them to expand if they can. So when we heat the air in this balloon, these balloons are not airtight, right? The bottom is open, and a lot of times there's a little bit of a hole at the top as well. When you heat the gas, the air, it expands, it gets bigger. And when it gets bigger, its mass doesn't change because it's the same particles, but they're spreading apart. There's more space in between. The volume goes up, the mass stays the same, the density drops. The density changes. Now the air inside the balloon is less dense than the air outside the balloon. And gases can float or sink in each other just like liquids can. So the lower density gas floats on the higher density gas, and it lifts the balloon up into the air. So if we look at the volume as a function of temperature, we see that as we increase the temperature of the gas, the volume increases. These sorts of measurements need to be done at constant pressure. If we take this, which forms this beautiful straight line, and we extrapolate means that we draw this line past the actual data. What we see is that it goes through zero volume at a temperature of minus 273 degrees Celsius. Is it possible to have a negative volume? No. No, it isn't. And you can turn something out inside out, but it still doesn't have a negative volume, right? You can't have a negative volume. So this is the theoretical lowest possible temperature. It's called absolute zero. And this was the basis for the Kelvin scale of temperature. The lowest possible temperature, minus 273 degrees Celsius. So Charles was looking at the relationship between volume and temperature. And this is quite a bit after Boyle. This is in the 1700s. He was a French mathematician and physicist and studied the relationship between volume and temperature. So his law can be states that the volume of a gas is proportional to the temperature. They're directly proportional when you use the Kelvin temperature. Let's go back to this this graph here. So do you remember what the equation for a line is? Anybody? Y equals what? mx plus b. What is b? The y-intercept. So if the y-intercept is 0, that would be good, right? Then y equals mx. Here, y is v, and x is pressure. Volume equals some constant, the slope of the line, times the pressure. If we've got an intercept in there, it's not directly proportional anymore. It messes everything up. So we always, always, always use the Kelvin scale so that we can get rid of that intercept factor. When we use the Kelvin scale, we've got a 0 intercept on the y-axis, and that makes the equations work out beautifully. So the volume of a gas and its Kelvin temperature are directly proportional. You double the volume, you double the temperature. So there it is, in all caps with exclamation points. And then I'm going to draw boxes around it too. Really, really important. The temperature must be expressed in kelvins. This is the most common mistake that students make when doing gas law problems is they forget to convert to Kelvin. They leave it in Celsius. So, yeah, I've taught off these slides too many times. I already talked about that, and I already talked about that. What temperature scale do we use for gas law calculations? Fahrenheit? Celsius? Come on, help me out here. Kelvins. Okay, right here. Kelvins. Kelvins. Okay, say it. Kelvins. What temperature scale do we use for gases? Kelvins. Thank you. It's really, really important. This is something you could try at home. Blow up a balloon and stick it in ice water. That's going to lower the temperature. The balloon will shrink. It'll get smaller. Take that balloon and stick it in hot water, and it will just magically get bigger. You can go back and forth doing that all day till the balloon pops. The hot water increases the temperature of the gases. The gas particles move faster, and they're going to cause the volume of the gas to expand. You cool it down in ice water, they slow down, and the volume gets smaller. So we can use Charles' law to calculate changes in temperature and volume. And this is a useful form of Charles' law. V1 over T1 equals V2 over T2. All temperatures must be expressed in what? Kelvins. Here's an example. A sample of gas has a volume of 2.80 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. What was its initial temperature in kelvins and in Celsius? Now what you'll see in most of these gas law problems is they'll generally give you the temperature in Celsius. I've never seen a glass thermometer that was calibrated in kelvins. Because the conversion, the relationship between Kelvin and Celsius is so simple, there's no point in making special thermometers. You just add 273 to the Celsius temperature. So again, we're going to follow the same idea of identify the numbers, put them in a table. So here's 2.8 liters, 0 degrees Celsius, and 2.57 liters. So the first number I come to, 2.80 liters. Liter is a unit of what? Volume. At an unknown temperature. Okay, well that's not a number, I'm going to skip that. When the sample is submerged in ice water at 0 degrees, its volume decreases to this. Do you see that these two numbers go together? These guys are together. This other one is with the unknown. So this is we've got temperatures in here. This is the unknown temperature. And then here I've got 2.57 liters, and I have 0 degrees Celsius. What do I need to do to that temperature? Convert it to kelvins. Let's do it right now before we forget. Plus 273. So this is 273 Kelvin. I didn't leave myself much room. I'm going to move that over. So that's 273 Kelvin. Let's finish off our table here. So here in the question mark, what should I call that? T1. So now I've organized the numbers that I was given. Now I need an equation. I need V1 over T1 equals V2 over T2. I need to solve this equation for T1. This equation has fractions in it, and the thing I'm looking for is in the denominator. Bad things are going to happen. People lose their minds when they do problems like this. So this is what you need to do. Get rid of the fractions. We do that by cross-multiplying. Have you heard of cross-multiplying? So we're going to take the top of one side. We're going to take this times this. And that's going to be equal to this one times this one. See the x there in the middle? X marks the spot. Cross-multiplying. The top of one side times the bottom of the other side equals the bottom of the first side times the top of the other side. If that bothers you and you don't believe me, I'll be happy to show it to you after class or during the break. So this gives us, I'm going to V1 T2, that's the orange ones, and T1 times V2. I'm just going to try to keep track of that guy that I'm looking for. Now I got rid of the fractions, it's going to be much simpler to rearrange this and come up with the correct formula. So I want to divide by V2. I want to do it on both sides. So V2 over V2 is 1, and those cancel out. So now my equation is T1 is equal to V1 T2 divided by V2. Again, take 5 seconds to make sure that you're copying the equation down correctly and not switching ones and twos. And then I'm going to plug my numbers in. So V1 on the top, 2.80 liters, times temperature 273 Kelvin, put the units in there, divided by V2, 2.57 liters. The liters cancel out. So 2.8 times 273 divided by 2.57 equals. Now, how many significant figures should that have? It should have 3. And what's the unit on that? Kelvin. So that's the temperature in Kelvin. And let's ask ourselves if this is making sense. So the sample had this volume at an unknown temperature. It was submerged in ice water. The volume decreased. Are we expecting the original temperature to be higher or lower than 273? Higher, right? Because it was warm and it got put in ice water. This is higher, and so that's a good sign. Because the common error is to get something upside down, and then it ends up going in the wrong direction. If you end up with your T1 smaller than your T2, something went screwy. But then we also have to find the Celsius temperature. So to get this into Celsius, we're just going to subtract 273. And we're going to get 24 degrees Celsius. Any questions?